The lunar south pole is defined by extreme geometry. Sunlight permanently strikes elevated crater ridges, while the basin floors below plunge into absolute darkness. Within these dark basins lie our highest priority targets, doubly shadowed craters. These are specific, deep microenvironments, shielded from direct sunlight and insulated from any scattered light bouncing off the surrounding crater walls. This high-resolution map shows the density and scale of that exact target region. The topography is rugged, highly cratered, and unforgiving for surface operations. Because these doubly shadowed craters block out all indirect illumination, they sustain the lowest, most stable temperatures anywhere in the region. That thermodynamic stability creates the ideal conditions to trap and retain water ice over geological timescales. This ice is the critical resource required to support oxygen production and hydrogen-based fuel generation for long-duration human missions. Accessing these craters provides the highest possible scientific yield in modern planetary science, but navigating a rover into these unlit, steep-walled traps poses a severe operational challenge. Orbiters like Chandrayaan-2 and the Lunar Reconnaissance Orbiter have already mapped this region extensively, providing a wealth of radar, optical, spectral, and thermal data. The friction point is not a lack of data, but how that data is processed. Mission control teams currently analyze these rich datasets in total isolation from one another. Radar analysts map subsurface signals. Terrain analysts independently grade slope hazards. Path planners manually reconcile conflicting priorities, attempting to guess at a viable route. Treating a lunar rover traverse as a standard shortest path problem ignores the physical reality of the vehicle. It bypasses strict energy limits, thermal constraints, and the actual scientific value of the terrain being crossed. Operating with disconnected data streams introduces unnecessary risk. To solve this, we propose the Lunar South Polar Mission Planning System, or LSMPS. It is a 7-layer AI framework designed to co-optimize ice detection, rover physics, and mission execution into a single, continuous pipeline. The architecture begins at Layer 1. The focus is specifically on the top 5 meters of lunar regolith, the depth limit of orbital radar, processing raw inputs like the circular polarization ratio. Look at this model. Rather than a rigid radar threshold, Layer 1 deploys an AI architecture fusing radar, optical, and thermal data simultaneously. The output is a continuous probabilistic confidence map, detailing the precise likelihood of ice concentration across the terrain. A simple percentage score is insufficient for mission commanders risking billion-dollar hardware. The system must provide auditable proof for its predictions. To achieve this, Layer 1 runs SHAP and GradCam algorithms to generate feature-level evidence. This isolates the exact environmental variables, like local temperature drops or specific radar backscatter values, that drove the AI to predict ice in that specific crater. By calculating exactly why a region contains ice before the launch is approved, Layer 1 ensures the rover targets a scientifically validated location. Layer 2 focuses on landing site selection. A destination is only viable if it is both operationally safe to access and scientifically valuable to explore. A random forest algorithm ingests the Layer 1 ice map, cross-referencing it against orbital slope data and boulder densities detected by object recognition models, outputting a ranked shortlist of coordinates. This topological mesh illustrates a prime target, the Shackleton-de Gerlache connecting ridge. It satisfies multiple constraints simultaneously, featuring low surface slopes and up to 92% cumulative solar illumination along its spine, while sitting directly adjacent to dark, high-yield microcraters. Layer 2 distills these variables into a mathematical landing safety score, ensuring all downstream surface operations are anchored in a physically survivable location. Traditional path planning often plots a route directly to the objective and calculates the required battery drain after the fact. Layer 3 reverses this, using the energy reachability envelope. It calculates reachable, safe return locations based on battery state. As terrain geometry shifts, like steep inclines or soft regolith, the energy cost increases, and this boundary dynamically shrinks to prevent overextension. Once the safe envelope is established, Layer 4 breaks the execution into phased, independent sorties, moving through reconnaissance, approach, and science stages, rather than attempting one continuous, high-risk drive. Before entering any permanently shadowed region, the rover must clear the Shadow Crossing Risk Protocol. This gateway verifies battery reserves, evaluates thermal tolerances, and communication lines of sight before a dark shadow is ever breached. By setting strict physical boundaries first and enforcing hard operational checkpoints, these two layers prevent rover stranding by design. With the operational envelope secured, Layer 5, the Science Opportunity Value Map, dictates the actual route. It challenges the assumption that a rover should take the shortest possible path. This pathfinding visualization highlights the system's logic. Instead of minimizing distance, the algorithm uses a weighted cost function to maximize the total scientific value collected per unit of energy expended. Layer 5 plans the ideal scientific route, but Layer 6, the autonomous rover safety system, is responsible for keeping the vehicle alive as it navigates the terrain. Standard robotics often use separate systems for traction control, obstacle avoidance, and slope stability. When operating independently on hazardous terrain, these systems frequently issue conflicting commands to the rover. Layer 6 resolves this by consolidating all sensor inputs, wheel slip, slope angles, and boulder detection, into a single arbitrated decision authority that governs real-time behavior. These layers ensure that every meter the rover travels yields high-value data while continuously safeguarding the hardware against dynamic surface threats. Despite the best planning, a rover operating inside a permanently shadowed crater faces severe risks. An unrecoverable hardware fault or critical battery depletion is a realistic end-of-mission scenario. If a critical failure is detected, Layer 7, the mission legacy capsule, activates instantly. The rover aborts exploration mode and shifts entirely into legacy mode. The rover autonomously selects a final resting position, prioritizing maximum communication visibility over physical safety, rotating to align its transmitters with the horizon. In its final operational sequence, the rover compresses and transmits the highest value scientific data directly to Earth, including ice confidence maps, sample analysis, and system logs, before its power is fully exhausted. Because the rover maintains a continuous mission snapshot at every waypoint, this final transmission is highly efficient. It only needs to send a small, compressed Delta package containing the newest data collected since the last upload. By engineering the mission as one unbroken pipeline, from the initial orbital AI detection down to the final data transmission, LSMPS ensures that even if a rover is lost to the shadow, its scientific legacy survives.